Hello, this is John Noguera. I am the Chief Technology Officer at SigmaXL. Welcome to our webinar called What's New in SigmaXL version 8. This is part 3 of 3, and today we will cover descriptive statistics, templates, and calculators. The examples that are used and the data sets are all in the workbook that comes bundled with the software. Our agenda, we will cover the descriptive statistics. Specifically, we have additional descriptive statistics, additional normality tests, the percentile report, percentile ranges, percentile confidence intervals, and percentile tolerance intervals. Also, outlier and randomness tests. Under templates and calculators, we have the one sample z-test and confidence interval for mean, the normal exact tolerance intervals, the equivalence tests, one sample, two sample for means, two proportions, and two Poisson rates. Also the gauge, type 1 gauge study and gauge bias and linearity study. Under descriptive statistics, the new features are available by clicking the dialog options button. So that keeps it clean. When you click the options, you are presented with the new features in version 8. So we have checkboxes for additional descriptive statistics, additional normality tests, percentile report and percentile ranges, percentile confidence and tolerance intervals, and outlier and randomness tests. So I'm going to switch over to Excel, and the data example that I will use is the customer data. And in this example, we're going to do descriptive statistics on overall satisfaction, which is the 1 to 5 overall satisfaction by customer type. So statistical tools, descriptive statistics. I'll use entire data table, and overall satisfaction by customer type. So this is the same as what you see in version 7 with the addition of the options button. However, if you click the options button and check select all, that provides you with all of the new report items. I should point out that when you do this, the column format is grayed out and the group category X2 is grayed out. So it's a cleaner format, row format, and only allowing one group category. We have some options here I'll talk about in a moment: interpolated or exact for confidence intervals, quartile or percentile. Actually, I'm going to change that to percentile. And under percentile tolerance intervals, again, interpolated or exact. I'll leave that as interpolated, and we'll talk about that in a moment. So the top part of the report is exactly the same as what you get in version 7, and this is the start of the new content under additional descriptive statistics. So we begin with the 5% trim mean, and the trim mean, the 5% trim mean, the highest 5% and the lowest 5% are excluded, and the mean is calculated with the rest of the data. This gives a robust alternative to the median as a measure of central tendency in the presence of outliers. It's a robust measure of central tendency. Standard error of the mean is the S over the square root of n. And by the way, in the PowerPoint slides, these are all covered here. Standard error of the mean is S over the square root of n, and that can be used, for example, to compute the confidence interval. Variance, simply the standard dev squared. Coefficient of variation is 100 times the standard deviation divided by the mean. And then we also have the short term or within standard dev that's used in a control chart. So in an individual's control chart or in process capability, you have this short-term standard dev. So we've added it to the descriptive statistics. And you can quickly compare by customer type. These are overall SAT scores for customer type 1, customer type 2, customer type 3. Then we have the additional normality tests. For the primary normality test throughout SigmaXL is the Anderson-Darling normality test. It's very powerful, so we use that pretty well throughout. However, we added some additional normality tests that are also popular. The Shapiro-Wilk, the KSL stands for Kolmogorov-Smirnov-Lilliefors, and that is, Shapiro-Wilk is used up to 5,000 if your sample size is 5,000. If your sample size is more than 5,000, that's as far as the Shapiro-Wilk algorithm goes, and so we switch over to the Kolmogorov-Smirnov-Lilliefors. Just another alternative to the Anderson-Darling that some people prefer, so we've added that. So you have the actual statistic and then the p-value. So you can see here for customer type 2 that we have non-normal data, and that agrees with the Anderson-Darling normality test for customer type 2. You can see the low p-value denotes that you reject the null hypothesis that the data are normal. So we have agreement on both type 1 as being normal, type 3 as being normal, and type 2 is not normal. The Dornick-Hansen test is an omnibus test, or a combined test that combines the skewness and the kurtosis. So there are a few options in this combined test. And the one we chose Dornick-Hansen because we actually use that same test in the correlation matrix, and you have the highlight recommending whether to use Pearson or Spearman. We use the Dornick-Hansen test there. That's a bivariate normal. Here it's univariate. So why would you want another test? The advantage of this particular test is that if your data have ties, if you have chunky data, both Shapiro-Wilk and Anderson-Darling are very sensitive to ties in the data, and they will trigger non-normal even though the shape of the data is normal. If the data, due to measurement discrimination or count data, if you have ties in the data, those other two, Anderson-Darling and Shapiro-Wilk, will typically trigger that type of data as non-normal, whereas Dornick-Hansen will not. Dornick-Hansen uses skewness and kurtosis, and therefore is a better choice when you have that so-called chunky data. In this particular case, the results are the same for Dornick-Hansen as well as for Shapiro-Wilk and as well as for Anderson-Darling. Customer types 1 and 3 are normal. Customer type 2 is not normal. Now, you'll notice, however, that Dornick-Hansen is not as powerful as the others. So if the data do not have ties, then you want to stick with Anderson-Darling or Shapiro-Wilk. Okay, so that's the additional normality tests. And we have the percentile report and the percentile ranges. Now you have the choice. You can actually just display the 25th, 50th, and 75th. This gives you the full percentile report. Now, as you can see here on the smaller numbers or the higher numbers, because of with a smaller sample size, you basically get to a point where the minimum and the maximum are being used. And so you can see that it's really not until you get to the 5th percentile and the 95th percentile that you can actually get a better representation of the true percentile value. We also have the ranges. So we have the interquartile range, which is used in the box plot. The height of the box plot is the interquartile range, the 75th minus the 25th percentile. Also, the interdecile range, IDR, 90th percentile minus the 10th percentile. What was popular at GE, the span, 95th percentile minus the 5th percentile. And the equivalent of plus or minus 2 standard deviations, 97.5 minus 2.5, 99 minus 1, 99.5 minus 0.5, and the equivalent of 3 sigma, which is the 99.865 minus the 0.135. So these are the percentile ranges. Okay, so you have your percentile, various percentile values, your percentile ranges, and then we move into the percentile confidence intervals. Now, I'm going to talk about the difference between exact and interpolated in a bit. Because you are dealing with non-parametric calculation, you cannot get exactly 95%. For example, you might have 93 and 96. In order to estimate the 95% confidence interval, what you do then is interpolation. And the details are in the appendix of the workbook. I would say that typically you would want to use the interpolated because that's going to give you your best estimate as to the 95 or whatever confidence level you want. And also notice for the smaller values, if the sample size is inadequate, you're given a report saying what the minimum sample size is. So for customer type 1, if I scroll up, I have 31 observations in that particular sample size. So that wasn't enough. I can't get a confidence interval for the 10th percentile. But I do have enough for the 15% mark. So these are confidence intervals for percentiles. The most commonly used one is the confidence interval on the median, which is the 50th percentile. But this gives you the full gamut of confidence intervals. And a little trick is that you can actually use the confidence intervals as one-sided tolerance intervals. And I'll show you how to do that in a bit. Now, down here we have the two-sided tolerance intervals. These are the percentile or non-parametric tolerance intervals. So two-sided non-parametric tolerance intervals. So what this says is that at the 95% confidence level, what interval will include 50% of the population? And so we have the range of values given for the 50%, 80%, and as soon as you get into the 90% of the population, we don't have a large enough sample size, and so you're given the report as to what the minimum sample size is. Okay, so that's the percentile tolerance intervals. And also a point is that if you have normal data, then we recommend that you would use the normal exact tolerance interval calculator, and we'll cover that in a little bit. I want to switch over to PowerPoint to talk about using the confidence interval to assess one-sided tolerance intervals. So for example, in the report here, this is my confidence interval at the 10% mark. This is my confidence interval at the 90% mark. So I can say that this value here, 2.58, is my one-sided lower tolerance interval, and this 4.97 is my one-sided upper tolerance interval for 90% of the population. Now there is one caveat, and that is that the confidence level is 97.5, not 95. If you want 95%, you'll have to change the specified value to 90%, and then that will split up, and so you'll have 95% one-sided and 95% one-sided. So that's just a little trick, converting a confidence interval to a tolerance interval. And recall the numbers that are given down here, these are the two-sided tolerance intervals. So that's the confidence intervals for the percentiles, tolerance interval for the percentiles, and a little trick to convert a percentile confidence interval to a one-sided tolerance interval. What I am going to do now is I'm going to go back to Excel, and I'm going to recall the dialog, and I'm going to change interpolated to exact and just discuss the difference between the exact and the interpolated. So here we see the report says exact 95% minimum, but you will notice in parentheses all the values are larger than 95%. So these intervals are saying we will guarantee you a 95% confidence level. The actual number is greater than 95%. So we call that exact 95% minimum versus the interpolated, which is the interpolated value, and it's the estimate of the 95%. Okay, so essentially it takes the above and below and interpolates to estimate what the actual 95% is. Okay, so that's percentile confidence interval, exact 95%, and percentile tolerance intervals, exact 95%, as a minimum or as a guaranteed value. Now, we'll look at outliers. So when you're looking at outliers, this is actually very similar to what we have when you run a one sample T or an ANOVA. You get this report with the green, yellow, red. And in this case, for customer type 1, there are no outliers using the Boxplot rules. And here we have a potential outlier. This would show up on the box plot as well. And that's the 1.5 IQR rule. We call that a potential outlier. I'll just go back to the slides here because I have a summary. So under the Boxplot rules, we have the potential is when a point exceeds the Q3 plus 1.5 IQR or Q1 minus 1.5 IQR. And then likely is the 2.2 IQR, and extreme is the 3 IQR. Okay, so these are the, you see these in the Boxplot rules. We don't actually have the likely in the Boxplot, so this is given in the report. This is the same as what you get when you do the assumptions test on a one sample T or a two sample T test or an analysis of variance. Grubs is a new addition, and it's more powerful to detect a single outlier, but it does assume that the remainder of the data are normally distributed. The randomness runs test is a non-parametric exact runs test, and as I mentioned, we use the same green, yellow, red highlight to make it easier to interpret the results. So if I go back now, we can see here that using the Grubbs test for this data, they're all fail to reject, so no outliers, and you can assume here that we have randomness. The data are random, so it's a fail to reject the null hypothesis that the data are random. What I want to do now is I want to modify the data a little bit, and I'm going to add an extreme outlier. I have a column of data, average days order to delivery time. And I'm going to take that and I'm going to add the value 100. So I'm deliberately adding an extreme outlier, and I'll select that data and I'll run the descriptive statistics with that data, average days order to delivery time, and I'm only going to look at the outlier in randomness tests. So here you get the report says, using the Boxplot rule, we have an extreme outlier. And excluding the outlier data are inherently normal. So it is testing that. It removes the outliers and then checks to ensure that the remaining data are normal. Here we have Grubbs test also indicating that that point is an outlier, and it's indicating here it's the maximum data value of 100 is an outlier. Of course, you would want to complement this with graphical analyses like box plots and run charts. And that concludes this section on the new features in the descriptive statistics. So now I will go back and introduce the templates and calculators. So in templates and calculators, we have the one sample z-test, tolerance interval calculator for normal exact, equivalence tests, also known as two one-sided tests, one sample for mean, two sample equivalence test to compare two means, two proportions equivalence test, two Poisson rates equivalence test, and the type 1 gauge study and the gauge bias and linearity study. This first one is pretty straightforward. With all the templates, you have to enter the summary statistics where it's shaded yellow, and then you get your results. The reason we added the z-test, it was something people were asking for, because you'd have students compute the z-test by hand, and SigmaXL didn't have a z-test in the software, so now you have a way of validating your hand calculations. In practice, you would typically use a t-test because the z-test requires that you know the population standard deviation, and the t-test is with the sample standard deviation, or the unknown population standard deviation estimated from the sample. So here you put in your sample size, your sample mean, your known population standard deviation, and you get your p-value. In this case, it's a reject the null hypothesis, and you also get the useful information, test information. In this case, you're rejecting the null hypothesis and you're concluding that the alternative is true. All right, so that's the one sample z-test. Now, the normal tolerance interval, let me switch over here because I want to demonstrate that. So that is available under templates and calculators under basic process capability templates. Or if you go to process capability, basic process capability templates, either location gets you to the new tolerance interval calculator. So here I have data that are assumed to be normal. In this particular case, I have a sample size of 30, a mean of 1, and a sample standard dev of 1. I specify the population coverage, and I specify the confidence level. And so what this calculator tells me is what is the tolerance interval that will include 99% of the population data at a 95% confidence level. So it's the same as what I was showing you earlier under descriptive statistics, but those were calculated using non-parametric methods, percentile methods. This is using an exact technique. If it's a one-sided, and you can specify one-sided upper or lower. If it's a one-sided upper or lower, uses the non-central t distribution. If it's two-sided, it uses the non-central chi-square. So you can look up the workbook to look at the details. Based on a sample of data, you want to be able to guarantee a certain minimum population coverage. And I want to go back to the slides here because this is the tolerance interval normal exact, and so it's very important that the data come from a normal distribution. You need to run your normal tests and verify that the data are indeed normally distributed. It's much like a process capability. There's no central limit theorem going on here. These are individual observations. If you have non-normal data, the tolerance interval calculator will not be correct. So what do you do if you have non-normal data? I'm going to present a few options here. First, you can consider using the Box-Cox transformation. And if you find a suitable transformation, then you take the transform data and then just apply it to the exact normal calculator. The disadvantage is that there are more steps to compute this because you have to apply the transformation and then you have to apply the inverse transformation to the calculated tolerance intervals. Also, you have the problem that the lambda parameter, that's whether you're squaring or taking the logarithm, whatever you're raising to the power of, there is uncertainty in that parameter. And that uncertainty is not included in the 95% confidence level. So you really need a fairly large sample size for this to be valid. So we recommend a minimum of 100, or if you have a theoretical basis for your transformation. So I give the example, if you have a gamma distribution with a large shape, then we know from theory that the cube root is a good estimate, a good transformation for that particular distribution. And then the other disadvantage is that there may not be a suitable Box-Cox transformation. So what about the Johnson transformation? Because that's even more powerful than the Box-Cox. However, the problem with the Johnson transformation is now there are 4 parameters, and the uncertainty in those 4 parameters is not taken into account when you, again, in that 95% confidence level for the tolerance interval. So we don't recommend the Johnson transformation. Also, it's trickier dealing with the inverse transformation for the Johnson. Now, you can always use the percentile tolerance intervals, as we discussed earlier. However, as we also saw, for smaller sample sizes, it may not be possible to compute the tolerance interval. And the intervals tend to be wider. So it does have the advantage that it doesn't depend on a specific or on any specified distribution. It's non-parametric, but you do have to have reasonably large sample sizes to get a good measure of a tolerance interval based on the percentile tolerance intervals. Another method that you can use is if you do distribution fitting, and I'll just show you here, if you run distribution fitting, one of the things that you get when you do non-normal distribution fitting is that you get confidence interval on the percentiles. And I'm not going to actually do this, but I'm just pointing out here that if you add, say, 1 and 99, then in the report you have a lower confidence interval and an upper confidence interval, so you can use these as tolerance intervals. The only thing is you have to have reasonably large sample sizes for these estimates to work 100 or so. All right, so that's the use of distribution fitting. So if you have non-normal data, you can use the box cops, you can use the percentile methods, or you can use these confidence intervals on percentiles that come from distribution fitting. But if you have a small sample size, then you're kind of limited. Then you're talking about Monte Carlo simulation, and that really requires specialized software. We are planning to incorporate that in DiscoverSim. Okay, so that's tolerance intervals. Now I want to talk about the equivalence tests, and I'll go back to Excel to demonstrate the equivalence test. This is under basic statistical templates. So I'll start with I'll skip the one sample. I'm going to go to the more common two-sample equivalence test. So what exactly is an equivalence test? Well, it's different from the normal paradigm for a test of hypothesis, because typically when you reject the null hypothesis, you're saying that something is different. Now, when you reject the null hypothesis, we're actually saying the two means are equal. So how do we do that? Well, we actually, with a little bit of trickery, used two one-sided t-tests. And if you reject both null hypotheses, then you can conclude that the means are the same. So what's the trick? Well, the trick is in this upper and lower equivalence limit. So you have the sample 1 size, sample 1 mean, sample 1 standard deviation, sample 2. You enter these values, but you then also have to specify an equivalence interval or equivalence limit. This is an equivalence limit establishes the zone or region of equivalence, and it's determined by what size difference is considered practically significant. So you, the practitioner, decide think of this like kind of like a guard band, is that what interval will I put in here that I can use and say if the difference in means falls within this interval, then I can conclude that these are equivalent. These two samples are equivalent. And these then are used to compute the p-values. Essentially, you're just running two one-sided t-tests. So you have a p1 value and a p2 value. So this is test 1 and this is test 2. And then we just take the maximum of p1 and p2. So if this is red, if we reject both null hypotheses, then we conclude that we have equivalence. Okay? And you can interpret either from the confidence interval, the 95% confidence interval is within the equivalence interval, or you can conclude from the equivalence p-value that equivalence is true. Okay, so that's the two-sample equivalence test. And we have a very similar with the two proportions. So I go to basic statistical templates, two proportions equivalence test. But now I'm dealing with proportions, and I specify my equivalence interval as a proportion. And same thing, if we reject the null hypothesis for both, we conclude that equivalence is true. There is one little catch that I need to point out. If you choose for your confidence interval method, the default is Newcomb-Wilson, which is the recommended confidence interval method. There may be, it may be possible that the p-value might give a different indicator than the confidence interval. And in that case, we recommend going with the confidence interval. If you use the normal approximation, then the confidence interval and the p-values will match, but it's possible that using one of these other techniques that there may be differences in the interpretation. So in that case, go with the confidence interval method. Also, we have under templates and calculators, basic statistical templates, we have the two Poisson rates equivalence test. So same idea, two one-sided tests being applied, and if we reject the null hypothesis for both, then we conclude that the two Poisson rates are equivalent. Okay, so that's equivalence test for two means, two proportions, and two Poisson rates. And we also have the one sample mean, which I'm not going to cover, but that's included in the new features. That now takes us to the gauge R&R. We're going to look at the type 1 gauge study and the gauge bias and linearity study. So we'll come back to Excel. If you go here under basic MSA templates, you'll get a blank template. But if you come over here under help, template examples, we have populated examples just to make it easier for demonstration purposes. So the data is already in and we already have the cells populated. This is the type 1 gauge study, which is a technique that is a precursor to a full gauge R&R study, repeatability, reproducibility. And sometimes you just need a quick and easy gauge study, and this follows the guidelines. We have references here, and essentially we use the highlighting on these, the gauge capability, CG, CGK. These are greater than 1.33. Your measurement system is capable, and resolution should be less than 5%. And you can click to create the gauge chart, which we already have done, but that just gives you the amount of variability for a part that is tested repeatedly. So that would be the same part tested repeatedly, and just gives you, as I said, a quick and easy way to assess the gauge capability. It's not a full gauge R&R study. It's not intended as a replacement, but it is something that can be done to get a quick assessment of or how the particular gauge is doing. Then you have your gauge linearity. So for that, we'll open up under template examples, MSA examples. I have from the AIAG example. This is gauge linearity report, so gauge bias and linearity study. So we have 5 parts. These are the known reference values, and if I click on the gauge linearity report, I have the graphical view. If the linearity is significant, we also show that by highlighting the bar chart in red. So this is telling you that you have the linearity is significant here. So you have 2 things, bias, and we look at the various bias values, but then overall we can see that on an overall average bias that's not a significant contributor, but whereas the linearity is in terms of % of process variation. If the regression line were flat or the slope was 0, that would indicate that there was no linearity. So the fact that we are seeing a significant slope, that tells you that there is actually an issue with gauge linearity. Okay, so that's the gauge linearity. You enter your process variation, you enter your part reference values, and you enter your part measurement data. You click the button, and you generate your linearity report. If the p-value is less than 0.05, it's highlighted in red, bold red, to indicate that it's significant, and the respective bar is colored. And statistical significance is the best indicator of a problem with bias or linearity. There are rules of thumb out there, but your best bet is to go with statistical significance. The dashed lines on the linearity scatter plot are the regression fit confidence intervals. If the zero reference line is not within the intervals, the linearity slope is significant, indicating that the measurement system linearity is not acceptable. And actually, that concludes our presentation. Thank you all very much for your attendance and your participation. We hope that version 8 serves you well, that the new features are things that you find to be very useful in your process improvement. And we are always open to hear other suggestions and recommendations for the next version. So we look forward to hearing from you. Thank you all very much.